Okay, so bear with me here, people. There's a wavelength to a dimensional gravity that is space and time. What it does is it holds up the mass and keeps it in place in order for an area to be held up by more than one type of inertia, if not just inertia. So then I multiplied that by e to the third, which is c volume squared. I put that added to the angular momentum of a mass, which is I think it's the orbit times the wavelength minus force centripetal, or orbit plus the wavelength times orbit plus the force centripetal times the wavelength. I forgot how I did it, but I did it. And it was then, after that, it's minus motion minus universal constant. A universal constant is something like the amount of energy spent out from, I don't know, anything like a sun or anything that gives off a constant force. So I found out one of them. It's like wavelength, but it's not six rows. It's 9. And I added a wavelength to it, and I multiplied it by time. Subtracted d squared, which is motion plus speed 2. I multiplied it by volume minus area. Subtracted speed squared from momentum of a planetary orbit. I got this, which is 9 triangles, 9 lines that equal, or not 9 lines, 9 triangles, 9 circles, and it seems to fit in an orbit that is stationary, cautionary, and in reverse. So without magnetism in the equation, the mass in general gets to be relative. Now, because we have magnetism in our lives from our planet, it shows that maybe we were lucky enough to get to where we are now, and I didn't put that down because that wasn't a part of the test of relativity. It was just to see if there was gravity involved, and so I figured this much out. A universal constant comes from E squared plus magnetism, then plus momentum of an orbit. So then it then leads out into the universe, or the planetary orbit, and it makes what it can, which is called space fabric. Okay, so thanks for learning with me, and I look forward to seeing you guys in school sometime soon. Alright, bye.